Physics H. I'm at home today. I'm going to make this video for you really quick. Kind of about problem 9 on worksheet 2. Now, I'm not going to do the exact problem as it is on problem 9, but I'll do something similar. So, the whole thing here is we're going to have an object launched off of some height, right, at some initial speed. We're going to figure out where it's going to land, right? How far it's going to land. Now, the height here, this is the height from whatever it's dropped, all right? And let's make that, let's put some numbers on it here to make things easy. Let's say this is a 40-meter high hill. Let's say I launch it at 20 meters per second here, all right? 40-meter high hill or cliff or building, whatever it might be. You're going to launch it horizontally at 20 meters per second. So we know it's going to go flying off and then hit the ground somewhere over here. This distance we're going to call delta x. Sometimes this is called the range. What's the range of the projectile that was shot? Now, here's the trick here. When something's launched horizontally, this velocity, so remember, we're going to have x direction and y direction here, right? This velocity is the initial x velocity, all right? So what we're going to do here is make a little organizational chart. 1, 2, 3, 4, 5. Do the same thing here. 1, 2, 3, 4, 5. Now that problem 9 has you fill in the whole chart, so we'll do that as well. V initial x, V final x, V average x, acceleration in the x direction, the displacement in the x direction, and the time in the quote-unquote x direction. Time doesn't have a direction, but anyway, V initial y, V final y, V average y, acceleration y, delta y, which is the vertical displacement, and time. So we've used delta x to represent displacement this whole time because we've just been moving horizontally. And even when we have moved vertically, like if we drop something, we still called it delta x. But we can't call displacement in the y direction delta x anymore because we're using delta x for the displacement in the x direction. So we're going to call it literally delta y. Now, the takeaway from the lab, right, the whole point of the lab was to prove that the acceleration in the x direction is always 0, and the acceleration in the y direction is negative 9.8 meters per second squared. Now, we usually will round that to 10, but for projectile motion, you know, if we're going to really try to figure out where this is going to land, we want to make sure that we've got that dead on, all right? All right, so negative 9.8 meters per second squared. So I'm going to start filling in these organizational charts up here. I know V initial x, all right? That's whatever speed it's launched horizontally with, since it's shot out from the edge of the cliff at this speed, and we know that's 20 meters per second, all right? Now, like we saw in the lab, right, remember the x velocity and time, it was just a constant negative value the whole video. Well, it's the same thing in this, but it's not constant negative because I've drawn it so it's positive. It's a nice constant positive 20 meters per second because the acceleration in the x direction is 0 meters per second squared. Again, we know this from the lab. These two things are always true about projectile motion. AX is 0 meters per second squared. AY is negative 9.8 meters per second squared. So, since the acceleration is 0, then the final x velocity is also 20 meters per second. The average velocity is 20 meters per second. So, great. Delta x, right, that's going to be the distance it travels. We don't know that. And the time it's in the air for, we also don't know. So let's go over and look at the y direction now. So what do we know in the y direction? Well, we know that the acceleration is negative 9.8 meters per second squared. So I'm writing kind of small here, a little bit hard to fit the units in there. What else do we know? Well, if it's launched horizontally, that's like something being dropped from that height. All right? It's going to fall now as it moves forward, and it's going to accelerate falling down. So the initial y velocity is 0 meters per second. We don't know the final y velocity. We don't know the average y velocity. Do we know delta y? Well, this is how far it's going to fall. So delta y here is going to be 40 meters. However, because it's going down, right, it's displacing itself down, delta y is negative 40 meters. So delta y is negative 40 meters. It's just however high the cliff is. Now, we got to figure out the time of flight, all right, to be able to get the range, delta x. We would also want to find v final y and v average y, but the time and delta x are what's important. So if you look over here, since we know the average velocity, we know delta x is going to be the average velocity times the time, right? We know that. So we got to get the time. I can't get the time from here. So let's see if we can get the time from the y direction. If you look back at your equations, right, we need one that has time in it. So we have, for ones with time in it, we have the definition of average velocity, which is displacement delta x, which is displacement over time, delta x over t. We have acceleration is change in velocity over time. We have displacement is 1/2 at squared plus v initial t. Then we have the v squared equation. V final squared equals v initial squared plus 2a delta x. Now, I know we use delta x, but anywhere where it says delta x here, we could put in delta y. All right, the vertical displacement. That, whether or not it's x or y doesn't matter. Delta x just means distance or displacement in this case. So I need to use one that has time, so this one's not going to cut it. V squared is not going to cut it. V average equals delta x over t. Well, that's what I'm using here. I can't use that to solve for time. All right. Acceleration, okay, then maybe we can use this. Acceleration equals change in velocity over time. Well, the problem is you can't mix variables from x and y, right? I got to stay in the vertical direction. However long this object takes to fall and hit the ground, that's how long it's going to have to move forward. So we got to stay over here. So delta v, we can't do because we don't know v final. We don't know v final. And I can't find v final unless I know the time. So we're kind of in a pickle here. So that one's not going to cut it. So let's look at this last equation. Delta x, that's what we're looking for. Well, no, we have that. Delta x is negative 400. It's delta y in this case. We know the acceleration, and we know the initial y velocity. So look, I'm going to rewrite this equation over here. Delta y, I'm going to put in delta y instead of delta x because it's vertical displacement, equals 1/2 ay t squared plus v initial y t. All right, this is awesome because I know v initial y is 0. This term's going to disappear. I'm left with these two. So I know this is negative 40 equals 1/2 of negative 9.8 times t squared. So look at that, one unknown variable. So now we just got to follow through with the math. And of course, I don't have a calculator up here. So what I'm going to do is I'm going to put in 10 for this just to make the math easier so I can get a decent estimation. So 2 times 40 is 80, so I multiply both sides by 2, right? So negative 80, and then I divide both sides by negative 10. All right. 10 to negative 80 by negative 10 is 8 equals t squared. So the time to hit the ground is the square root of 8, which is probably like 2 point, oh, I don't know, 2.4 or something, wild guess here. Let's just say it's 2.4. Radical 9 would be 3. Radical 4 would be 2. So somewhere in between the two. It's probably more like 2.6 actually, something higher. So let's call it 2.6 seconds. I don't have a calculator handy at all, but let's say it's 2.6 seconds for the time. All right, just radical 8, whatever that might be. Well, 2.6 seconds. that goes in both times, right? So I know the time of flight is 2.6 because that's how long it's going to take to hit the ground. So I can put that over here in the x direction. Remember, I'm keeping these separate. X and y, I'm keeping separate. And I kind of kept them separate like this as well. So now that I know the time, I can take it over here. And I could say delta x equals 20 meters per second times 2.6 seconds. So 2 times 2.6 would be 5.2. So delta x equals 52 meters. So it moves 52 meters forward while falling down 40 meters. That's pretty cool. Now the final thing here is to finish filling out this table, we need the final velocity, final y velocity. So in order to get that, I'm going to back up. Alright, I had that equation over here that was acceleration equals change in velocity over time. Right? And I can solve this for final velocity. V final equals V initial plus AT. You multiply both sides by T. Delta V is V final minus V initial. You end up here. This term's just 0. So you get V final equals acceleration times time, or negative 10. I'll put in 10 here times 2.6 seconds. So V final Y is negative 26 meters per second, which would be an average velocity of negative 13 meters per second. Alright, so that's pretty cool. Got that whole table filled out. It's really what we've already done in terms of solving equation motions, but you have to break it in two parts because of the forces involved, right? The forces are two-dimensional. We have a y force and we have no x force. So the x direction of motion, the acceleration is 0 because there's no net force in the x direction. The y direction, the acceleration is negative 9.8 because we do have a net force in the y direction caused by gravity. All right, that causes the velocity in the y direction to change. The x direction, the velocity stays constant. So this is a repetitive process, these problems. We pretty much always solve them this way, where we, draw the diagram, we think about the speed it's launched at. Sometimes we're not given the speed it's launched at, right? And we actually are given the height and how far it ends up, right? So if I know from 40 meters, no matter how fast it's launched, it's always going to take that 2.6 seconds to hit the ground. Man, I wish I had a calculator right here. I'm looking. I have a little desk behind me. Ooh, what's this? Look at this. What's this? Does this have square root? Look at that. Oh man, this happened to be just sitting in the little bin behind me. Look at this old thing. All right, let's figure it out. We were taking the square root of, what was it? Of 8. 8 square root is 2.8. Oh man, I was way off. 2.8 was closer to 3, not 2.6. So you can change that all to 2.8 meters per second. The distance here now is 56. All right. Look at that thing. It's a beaut, actually. I've had this for years. My wife got it somewhere along the way. Look. Harman 213. I must have had this at school for a while. Wild. Anyway. That's fun. Anyhow, this is a repetitive process here where we are given a couple things to start off with, and then we have to figure out where they go into these tables and figure out what we're looking for. Sometimes, like I said, we're given the range, where it lands, and how long it took to hit the ground, right? So if you know how long it took to hit the ground and how far it landed from the edge of the cliff, right, you could figure out the speed you shot it with. And as long as you know how long it took to hit the ground, you could figure out the height of the cliff. So there's all different ways to do this, and that's what we're going to do over the next few days, is practice different ways of looking at these problems. And then we're going to have an awesome lab where you're going to have to figure out where a ball is going to land if it gets launched off the side of a lab table. Okay? So anyway, have a good one. Good luck to you. You'll be watching this 10th period. Talk to you later. See you Monday and Tuesday.